Hello there. Good afternoon. Oh, I'm shouting at you, sorry. My name is Nina, and I'm delighted to welcome you to this afternoon of all things quantum. Here at the ArtScience Museum, we are, as you probably know, dedicated to the exploration of art and science and culture and technology. So I think you can imagine just how proud and excited we are to be a part of the Quantum Short Film Festival now for the second time. It's a lovely collaboration with our dear friends at Center for Quantum Technologies at NUS, and we're super excited about this year's selection of films, which are, very, very exciting. So one of the interesting projects that started us, that we've been talking to Jenny at Center for Quantum Technologies about, is the exhibition downstairs in B2, which is a celebration of Richard Feynman's 100 years. Richard Feynman is supposed to have said that if you think you understand quantum, then you don't understand quantum, which is a source of great relief for me personally, because I'm somewhat lost in all of this. Since we launched the project to mark what would have been 100 years of Richard Feynman, we've sort of launched ourselves in and tried to understand Richard Feynman's world and his many ideas, and we have got used to maybe some of the paradoxes and the vagaries and the creative potential of quantum ideas. And we've been guided very patiently by Jenny and her colleagues at CQT. They've been our, if you like, our sort of knowledge partners on the exhibition project. And I think it's therefore very fitting, and certainly from our point of view, with the greatest pleasure that we now, as we go into the last couple of weeks of the exhibition, can stand here and celebrate again the spirit of Richard Feynman and his quest for discovery and his sort of discovery of new ideas and new diverse disciplines, his playfulness as well, which I think are qualities that come through in the films we're going to see today. So, with no further ado, I'd like to welcome Jenny Hogan to the stage so she can tell you a little bit about what CQT does and introduce the speakers. Here you are, Jenny. Feels very loud.
Hi, thanks everyone for being here this afternoon for this special Quantum Shorts event. As Nina said, we've been working with the museum for a few years, and most recently, particularly on the exhibition All Possible Paths, Richard Feynman's Curious Life, which is downstairs if you haven't seen it yet. Now, I'm Jenny Hogan from the Center for Quantum Technologies at the National University of Singapore, and I'm kind of coming out from behind the scenes of the Quantum Shorts Film Festival to be here. So with my colleagues at CQT, as I call it for short, I've helped to run Quantum Shorts since 2012. So that year we had the idea to run a competition for quantum-inspired films. The next year we thought we'd mix it up a bit and we ran a competition for flash fiction. The year after that we went to films and so on, you get the idea, until this year it's our 7th edition and you're here to be part of our film festival. Now I need to be clear that most of my colleagues in CQT are not in the film and fiction business. So we are a Singapore National Research Centre of Excellence. We were established in 2007 with support from the National Research Foundation and Ministry of Education. So we have about 150 physicists, computer scientists, and engineers, and we do basic research in quantum physics. That means we're trying to study how the particles of light and matter behave, and then we also ask why do they behave those ways. Now, sometimes when you do this kind of curiosity-led research, you learn things that turn out to be useful. And that has been the case with quantum physics. So in fact, particularly when you combine it with information technologies, there are some useful things you can do. So some of the scientists at CQT are working on new ways of encrypting data, of doing computing, and of making very precise measurements. So there's a whole new generation of quantum technologies coming to the world. So why, you might ask, does it make sense for this bunch of scientists to run Quantum Shorts? Quantum physics has long provided inspiration for artists and filmmakers, writers and philosophers, but what do we scientists get out of encouraging them? So we have a few reasons. One is that we think science should be considered part of our culture. We also want to show that science is creative. So when you do research, it's not like when you do your maths and physics homework at school and every question has a right or wrong answer. Research is actually about finding the questions to ask, and you have to find questions that people don't know the answers to, at least not yet. And last but not least, we want to give people a way to engage with some of the ideas that our scientists work on, to feel some of the inspiration that comes from understanding just a little bit about the universe, and to think about the technologies that this understanding makes possible. So stories, whether they're told through film or prose, are a powerful way of sharing ideas and starting conversations. So from the first year of Quantum Shorts, we've been really amazed at the quality and creativity of the submissions that we've received. So in response to our call for quantum-inspired films last year, we had 176 entries. Today, you're only here to watch 10, so these are the finalists, selected by a panel of shortlisting judges. And those judges are scientists, artists, and communicators who represent some of our partners in the festival. We're lucky to have quite a few of them here today. So Nina, that you just heard from the ArtScience Museum, is one of our judges. And we have two others, but before I introduce them, I'm just going to take a moment to thank the partners that we've worked with. So we've been privileged to have long-standing support from two media partners, the popular science magazine Scientific American and the scientific journal Nature. We also work with an international network of scientific partners, other research centres, in Australia, Canada, the UK, the Netherlands, New Zealand, and the United States. And we have screening partners, including today's host, the ArtScience Museum at Marina Bay Sands. So we're deeply grateful to all these partners for making the festival a success. And I'd like to thank the museum team particularly for making the event here today possible. Oh, thank you. Now, if you haven't already checked your program, if you picked up the booklet, this is what's going to happen today. So next up, we have two short talks by Dr. Michael Brooks, a journalist, and Dr. Dagomir Kazlikowski, a theoretical physicist, who are both members of the Quantum Shorts shortlisting panel. They're going to share a few stories with you about physics in film and about quantum physics concepts. After that, we'll watch the 10 Quantum Shorts films all in a row, and stay on at the end of this because we're going to have a panel discussion, and we're delighted to have two finalists who are based here in Singapore joining us for that. So you can look out for those two films for Singapore, and please save up your questions for the panel. So I'm now going to pass the floor to Michael, but first a few things you should know about him. So he followed up a PhD in quantum physics with a career as an author, journalist, and broadcaster. He works with CQT on outreach and is a consultant at New Scientist magazine. So he's written more than a couple of books, including At the Edge of Uncertainty, The Secret Anarchy of Science, and The Quantum Astrologer's Handbook. He also co-hosts a podcast called Science-ish that delves into the popular science behind popular culture. So after his talk, maybe you'll want to check that out. Anyway, Michael.
Thank you very much, Jenny. I'm just now going to set a clock so that I don't embarrass myself by taking all the time available to everyone. I work as a science journalist, as Jenny said. I also am a consultant to CQT, which is a long-running thing for me, which I love, the fact that I get to come to Singapore. And I also love the fact that I'm allowed to come here today. So thanks very much to the ArtScience Museum for the invitation to be here. It's fantastic. I'm going to talk to you for a few minutes about the physics that we find when we go to the movies. Now, this might not be something that you actually think about very often. You might not go to the movies to learn any physics, and to be honest, it's very true that you probably won't learn much physics if you go to the movies. But as Jenny mentioned, I work as a journalist. I also run or co-host a podcast called Science-ish, which I think, yeah, I've got a little plug for it there, and obviously there'll be plugs throughout this entire talk. So this is a podcast where my co-host and I, Rick Edwards, we talk about the science in the movies, but not in a critical way. So you can often sort of find things, certainly on the internet, that say, oh, they got this wrong and they got that wrong in that film, and you know, Sandra Bullock's hair wouldn't move like that in microgravity, or you know, why can we hear the lasers in Star Wars when actually you can't hear any sound in space? So the laser cannons don't really make that sound in that there's no air for them to move through. But that's not very interesting, and that's not a very positive way to talk about what you can do with science in Hollywood. And we're very interested in what actual ideas come across from some of these films. Now, the most important thing when you're writing and directing a film is that you actually have a story to tell. and the story comes above everything else. But actually, that doesn't mean that you can't explore certain scientific issues. And when they come up in Hollywood films, they actually are there for a reason. They're there because the writer and the director actually find them incredibly interesting. We've been privileged on Science-ish to have input from a few directors, and most recently we had Juan Antonio Bayona, the director of Jurassic Park Fallen Kingdom. He talked to us for the podcast, and the shameless plug here, they actually came to us, amazingly. So we got to talk to him about what it was like and what motivates him. And of course the Jurassic Park franchise is all about de-extinction, and making creatures that are extinct come back to life. And Bayona was very interested in this, and he said it was one of the motivations. The ethics around doing this kind of thing, if you see Fallen Kingdom, it's actually all about the ethics of what you should do with these things and whether it's right to do it or whether it's not right to do it. And he said this was a big motivation for him in tackling this subject in the film. I'm sure that the $187 million budget of filming in Hawaii and the all-star cast had very little to do with his motivation whatsoever. But it's interesting to kind of get this idea that actually Hollywood does have films in it. Obviously Jurassic Park is to do with biology. I'm here to talk about physics. But I actually I've got 5 films lined up where I'm just going to talk about the physics that you'll find in them, the physics that kind of gets explored, or at least gets raised by watching this film. If you watch it with that kind of head on, where you're kind of interested in what are the issues behind this film rather than just what's the story. So we're going to look at Interstellar, The Martian, everyone's favorite, Back to the Future. I hope it's your favorite, it should be. The Core, which may not be your favorite. And Chain Reaction, which is almost certainly not your favorite movie. But these are all interesting from a physicist's point of view. So let's start with Interstellar. This is an extraordinary film. I love this film. I have to say, I think Christopher Nolan did an extraordinary job, but of course he has to tell a story. And so there's great physics in there. There's also terrible physics in there. So there's a line in the film where I think it's, yes, so the line is, "Love is the one thing we're capable of perceiving that transcends dimensions of time and space." Now, as far as I know, that's not true. And if you've ever had a long-distance relationship, you'll definitely know it's not true. But it's a wonderful film in that it allows us to explore general relativity, Einstein's theory that describes how space and time are changed by energy and by mass. It allows us to explore hidden dimensions of space. It actually allows us to look at the ideas. So they go in search of what Matthew McConaughey keeps calling the quantum data. We've got to find the quantum data. And it's somewhere there at the surface, the event horizon of a black hole. And actually, it's really interesting because we do need quantum data. And physicists who are trying to put together a single theory to describe the whole universe, joining Einstein's theory of relativity together with quantum theory, this is something that will require us to have a much better understanding of how quantum and space-time interact. So that kind of idea that the quantum data at the black hole, the boundary of the black hole and normal space, actually it sort of stands up to a little bit of scrutiny. It's a really interesting film from a physicist's point of view because the original screenplay and the original idea came from a physicist, a man called Kip Thorne. And he had the idea that you could use these kinds of ideas to explore something interesting in a movie. And one of the most interesting things that actually came out of this whole process is that Kip Thorne and his team of physicists got scientific publications out of the work that was done in order to create this movie. So astonishingly, in order to create those pictures of the black hole, which you might be familiar with, I think this is probably the most iconic sort of picture from the movie. This is the black hole called Gargantua. And it was created by Kip Thorne and his team of physicists giving Hollywood CGI people and their massive supercomputers all the equations of physics that would feed in and produce what a black hole would actually look like. And so what came out, they used 800 terabytes of data. It was an enormous, enormous sort of endeavor. The production company that did this was called Double Negative, and I think some of the work was actually done in Singapore here. They have branches in Singapore, London, and Vancouver. So there's a kind of local connection here. So they came up with this, astonishing-looking black hole, and this is apparently what a black hole would look like if we saw it from a distance. And it's lovely and realistic. Actually, it's not terribly, entirely perfectly realistic, because it turns out that when you do the physics, you get certain things come out which film directors don't like. So what you actually find is that the real black hole would have been slightly less red, basically. So, sorry, slightly redder than what's appeared in the movie because of things called the Doppler shift and the change in effects of light as it escapes the black hole. There are also issues, Christopher Nolan didn't really like how that looked. He didn't like the fact that actually the real black hole, the equations give you a slight sort of asymmetry. So one side of it, the black hole, in order to have these massive time dilation effects in the movie, where time is running at different different rates, allowing people to kind of travel between various things, it meant that that black hole had to be rotating at almost the speed of light. And when it's rotating at almost the speed of light, actually the effect that you get is that one side of it kind of disappears. So the light from it disappears. So you get these kind of effects. Christopher Nolan didn't like that either. And so he changed it and said, no, we're not going to have that. We're going to have it look like this original image because he didn't want the audience to wonder why the black hole wasn't symmetrical. I'm not sure any of us would have actually sort of sat there and wondered about that, but there you go. So what was really interesting is that all these various different aspects of what the black hole would look like, its redness and its asymmetry and everything else, were eventually published in a couple of scientific publications by Kip Thorne and his team. So the fact that they had access to Hollywood CGI supercomputers meant that you could do extra physics that you just wouldn't have been able to do otherwise, which is a marvelous thing. I should just mention, the one person who's not very happy with the whole outcome of how Christopher Nolan showed this film, showed this black hole, was a man called Jean-Pierre Luminet, who's a French physicist, who had actually in the late 1970s done some calculations on what black holes look like on an IBM punch card computer. So this was, pretty primitive. This was not Hollywood supercomputers at all. And he actually ended up, he didn't have a printer that would work in order to produce the output of his thing. So he ended up drawing the output that he saw in numerical form by eye using India ink, and then turned it into a negative. This is the outcome he got. So actually, his punch card computer gave him this incredible image here that he had to draw by hand, but you got that asymmetry that came out in the Hollywood supercomputers. So this was 1979 that he produced that. I thought that was wonderful. So that's Interstellar. The Martian. The Martian is one of those great movies, I think, one of the many movies in which somebody has to rescue Matt Damon. It seems to be an ongoing theme. I'm not really sure why. The one bit of physics that really sort of resonates in the film is when Donald Glover's character is trying to explain how you're going to get a spacecraft back to rescue Matt Damon. And he explains that you're going to need something called the slingshot effect. I'd say I don't really like criticizing movies. I mean, one of the things is that he's actually explaining this to the director of NASA. And the director of NASA would know what a slingshot was. So it's kind of for the purpose of the audience, because NASA has been all over slingshotting. Slingshotting is this amazing thing where you can use the gravitational pull of a planet in order to speed up or slow down a spacecraft. So you can find your way through space and get extra power just from coming in close to the orbit of a planet. You can pick up speed, or you can lose speed. And this has been something that NASA's been doing for a long time. So the Voyager spacecraft, for instance, did a slingshot past Jupiter and Saturn in order to escape the sun's gravity. And when you do a slingshot, what you do is you come in close, and the orbit of the planet as it's moving basically pulls you in. So you're pulled in by the gravity, but because it's moving as well, it pulls you in even faster. So you get pulled along, effectively, with the planet. And you can use this to accelerate, and then you can kind of, if you get in close and burn your thrusters at just the right time, you can get this extra speed and then go off in a different direction. And this is something that NASA does all the time. So you're sort of transferring a little bit of momentum from that planet or from that object. And actually, if you did it enough, millions and billions of times, you would actually stop that planet. You would slow it down so much that it would eventually, its orbit would decay and it would end up falling into the sun. I don't think NASA's at that stage yet. But here's just one example of what NASA has done that kind of is echoed in The Martian. So this is the Cassini probe, and it did a number of sort of swing-bys of various different planets. So it did an Earth swing-by, it did a Venus swing-by twice, it went past Jupiter. All of these things to kind of tailor its orbit to exactly what was needed without having to load it up with loads of fuel. So that's a great example of a little bit of physics in the middle of an action movie that you might not really have noticed, but is actually, really incredibly precise and true to real life. Talking of true to real life, let's just have a quick look at Back to the Future, which I have to say isn't really true to real life necessarily. What's really interesting about Back to the Future, though, is that all physicists, Stephen Hawking famously said this, he said basically all physicists want to work on time travel, but they're not allowed to, so they have to dress it up in different ways. So all physics research, you could basically pull back to physicists just wanting to explore time travel. So Back to the Future, as we are so aware, 1985, a wonderful kind of take on what happens if you have a time machine and all the problems that come in with this. And actually, we can travel through time in theory, although it seems like a ridiculous thing to say. The theory of relativity says that you can bend space and time in such a way that you can actually create a shortcut through space and time and find yourself in a different era. So the idea is basically this. You use a lot of mass or a lot of energy to bend space. And you can bend space and time around on itself if you have enough mass and energy. And if you have a wormhole, and I'm aware of the ifs coming up here, by the way. If you have a wormhole that you've got here, which is a kind of break in space-time, you can have a tunnel that runs through two different regions of space-time. And you can put them together, and you get this thing called a closed time-like curve here. And this means that you can travel basically without traveling through space, you can travel through time, as Marty McFly does in the DeLorean. And so in theory, there's nothing in the theories of physics that we have at the moment that says this is impossible. It's just quite difficult because A, you need to find a wormhole, and B, you also need to keep that wormhole open. And space-time has this elastic tension. Creating a wormhole is a bit like stretching an elastic band, and it just wants to stretch back and be closed again. So you need something called negative energy. And we're not actually convinced that this exists either. So as I said, there's a lot of ifs here, but nothing sort of fundamentally says that you can't do this if you could access all these materials. So we can travel through time. This is the famous flux capacitor that Doc Brown uses in the DeLorean as its time machine. Now this sounds fantastical and ridiculous, but let me just tell you that actually there's a man in Connecticut who's working on something similar. It's not called a flux capacitor. In fact, I'm not even sure he's given it a name. But this is Professor Ronald Mallett, who works at the University of Connecticut. He's a professor of general relativity. And he has actually been working on a time machine since he was 10 years old. And the extraordinary thing is that 10 years old, his father died of a heart attack. And the 10-year-old Ron Mallett was reading H.G. Wells' The Time Machine, and sort of had it in his head that if he could only work out a way of actually creating a time machine, he could go back and do something about this. It's a sort of tragic and romantic story, such that actually Hollywood are making a film or trying to finance a film about this attempt, which is an extraordinary kind of meta thing. So Ron Mallett is actually sort of in discussions with Hollywood producers about making a film of his childhood dream, which was to invent a time machine. And so he educated himself, and he did a physics degree and did his PhD in general relativity and became a professor working at a university in order to kind of fulfill this childhood dream. And this is his machine that he's come up with. Now, obviously, it's not big enough. It's not a DeLorean. It's not big enough to get into. But this is using a collection of lasers whose energy bends the space and time around them. And the idea is that the geometry of his machine and the energy of his lasers is enough to kind of warp space-time into that closed time-like curve. And this is an ongoing project. And as far as I'm aware, he hasn't sort of traveled through time yet. But this is something that sort of mirrors this amazing sort of lovely story in Back to the Future is mirrored in this real-life example. One more thing, this wonderful photograph, this big premise in Back to the Future where people are disappearing from the photograph because of the problems with time travel and the way it messes everything up. It turns out that actually you can avoid this using quantum mechanics. I'm not going to talk about quantum mechanics. Dag's going to do that in a moment. But quantum mechanics actually allows you a way of building a time machine in that if you follow the many worlds theory interpretation of quantum mechanics, when you travel through time, you will actually travel to a slightly different universe, a parallel universe, a different region of space-time in which you're not you, but a copy of you. And so the classic kind of thing that people talk about is the grandfather paradox, where you go back in time and you kill your own grandfather, and then you can't possibly exist because your grandfather didn't exist, which is a very bizarre thing to do, to be honest. But the idea would be that in the parallel universe, in the many worlds idea, you actually end up in a different universe with a different grandfather, and it's not actually your grandfather, it's the grandfather of you in the other parallel universe. It's complicated, but it's a way out. Chain reaction is something that that I think people sort of ignore this film. I think it's got some merit, actually. It's quite interesting. It's quite a good action movie if you've never seen it. 1996, so it's slightly dated. It's Keanu Reeves, so that puts a few people off, I know. But you remember how good he was in The Matrix, please. So chain reaction never actually talks very explicitly about the science that's within it. But the idea is to create this immense source of energy from fusion. And they're doing something which I think is basically bubble fusion in this, in that they've got some kind of thing going on in water, and you've got these bubbles, and then everything starts shaking, and then basically an entire city block explodes because there's so much energy suddenly released. This is hopefully not how it's going to work when we do develop fusion. But we are developing fusion. And so the idea is that actually you get this situation where you can release the energy that's in the nuclei of atoms, so right at the center of atoms. Of course, by nuclear fission, where we have a nuclear reactor or an atomic bomb, you release it in a very uncontrolled way. But if we can do fusion, actually where we sort of fuse two of these nuclei together, then actually you can control the way the energy is released. So it all comes from this reaction here. And the idea is that you take deuterium, which is heavy water, effectively, heavy hydrogen, which you can find in seawater. And it turns out that actually every cubic meter of seawater has 33 milligrams of deuterium. And so if you take a whole cubic meter of seawater, and you could release the energy from that that's equivalent to 10 barrels of oil. So these are the kind of statistics that fusion scientists are bandying about, saying this is why we want to do this. They've been trying to do it for a long time. The tritium, there's actually only, I think there's 20 kilograms of tritium in the world at the moment, so that hardly any resource, really. But the idea is that the reactor, if you build it properly, will create more tritium. So you can have deuterium, you can have tritium, and you fuse these nuclei together, and you get a lot of energy out and a few sort of products, some of which are radioactive, but it's nowhere near as bad as a standard fission reactor. And so physicists have been working for decades to try and create something along these lines. And the current project that's going on in the south of France at the moment is called the International Thermonuclear Experimental Reactor, ITER. And this is a tokamak, so it basically creates within a sort of a donut shape. You fill it with plasma that's created through fusion, and you get the energy out of it. So this is currently under construction. It's a massive international project, so China, Japan, South Korea, Russia, the EU. I don't know where Britain stands in it, because who knows after 29th of March. But it's an international collaboration. This tokamak is huge. So this is I think it's ridiculous, 73 meters tall. So it's a huge structure, and the idea is that if they can get this to work, then this will prove the principle that we can create a reactor that will release fusion energy, and you'll effectively be getting more energy out of it than you have to put into it, so we can use it as a massive energy source. And so although it's not quite on the scale of what happens in chain reaction, at least there is some kind of basic science in there. So we have some physics. The Core is not a film that many people are sort of very fond of particularly. It's a slightly ridiculous premise. It basically said strange things are happening to the magnetic field on the surface of the Earth, and then we find that actually the magnetic field just disappears. And the scientists in the film say this is because the Earth's core, the molten iron, which is sort of churns and circulates and generates our magnetic field, it's just stopped moving, it's gone still, and so they decide they're going to have to drill down right to the core of the Earth, getting slightly ridiculous already, and then use a load of nuclear bombs to restart the circulation of the Earth's core. Easy. Almost as easy as like flying out to an asteroid in Armageddon and putting a nuclear bomb in that and blowing that up. So the Core is kind of a ridiculous premise, but actually in the last couple of weeks there's been a lot of talk about the fact that our magnetic pole, our magnetic north, is actually moving around in a really random, difficult to understand way. So the magnetic North Pole is nowhere near the North Pole. A few decades ago, it was actually in Canada. It's now moving towards Siberia. It's sort of moving northeast at the moment because of stuff that's going on in the actual core of the Earth, the churning and the way that the molten metal is moving in the center of the Earth. It's changing the way the magnetic field is manifesting at the surface of the Earth. So our pole is wandering around, and we have to actually correct, you know, the kind of from the compass readings in order to be able to navigate properly. And nobody really knows why this is happening. We do numerical simulations on computers that try and get to the bottom of what's going on and why would the field be doing this kind of thing. We also build physical models of this sort of roiling molten metal, which are extraordinary things. So that in Maryland, there's a 3-meter ball of liquid sodium that people sort of churn around. Sodium's a pretty dangerous metal. 3 meters of it, molten at high temperature, no thank you. But so there's sort of various attempts to try and understand this, but we don't really know what's going on. And what was really interesting is that 2 weeks ago, a paper was published in Nature Geoscience, a journal called Nature Geoscience, where actually the researchers have shown, looking at the kind of magnetic rocks in the Earth's crust and the way they've changed and the way their orientation has changed over the years, they said that actually there was a time, 564 million years ago, when the Earth's magnetic field looked like it was about to fail, just as it does in the core. So this is sort of absolutely bang up-to-date science, published in the last month. It's saying that actually the scenario of the core, where the Earth's magnetic field sort of fails, actually almost happened 565 million years ago. And their interpretation of the magnetic rocks is that actually what happened is that there was a time when there wasn't a solid inner core to the Earth. So here on the left, as you see, there's hardly anything here at the center. And there was a very weak magnetic field at this time. This is the magnetic field in blue. It's lovely to note, by the way, how they've used the same color scheme as the poster for the core. So it's really, I don't know if that's subliminal, if that's just what you do for this kind of geoscience, but it's exactly the same set of colors, which I thought was lovely. And then what they're saying is, at some point, the inner core started to solidify, and you've got this huge sort of solid iron inner core on the right, as you'll see it there. And this sort of strengthened the magnetic field. You see those blue lines sort of much further out. And actually, the magnetic field is really important for protecting us from the solar cosmic radiation, the various sort of radiation particles that would increase the problems that we have with UV exposure, for instance. And it's interesting to note that Mars used to have a strong magnetic field and also lost its atmosphere, because that solar wind, those particles actually blow your atmosphere away if it's not held in place by a magnetic field. So we have to be very grateful that we do have a magnetic field. And I like the fact that there's this parallel between this Hollywood disaster movie and actually what really seems to have gone on, albeit 565 million years ago. So that's my quick guide to some physics in films. I haven't talked about Ant-Man, which Ant-Man and the Wasp, as well as the most recent one. These are full of quantum physics. And actually, the scientific advisor to those films was one of our shortlisting colleagues, so extraordinarily. So this is full of quantum physics. And, you shrink a man down to the scale of an ant, and you have to deal with quantum physics, apparently. And I love the fact that it's all in there. But I'm going to let Dag talk about the quantum side of it. So thank you very much for listening. Thanks.
Okay, thank you, Michael. Who knew how much physics you could learn at the movies? So the films that we have today are not Hollywood, but they are using quantum physics, all quantum physics. And to give you an introduction to that, I'm going to invite to the stage my colleague from CQT, Dagomir Zukowski. He's a principal investigator with our center. He's an associate professor at the National University of Singapore. And he's going to give you a glimpse into some of the kind of most important and crazy ideas in quantum physics so that you can watch the quantum shorts films with context. So as well as being a theoretical physicist, he's actually a filmmaker. So he's had short films selected for the international festivals, including the LA Shorts Fest, and he also makes films inspired by physics. So his latest feature-length project, we hope is coming soon, called The Zeno Effect. You might like to find the trailer online. Okay, Dag.
Thank you very much. And I have a very ungrateful task to teach you about quantum physics in 20 minutes, and I don't think it's possible because I've spent the last 25 years trying to understand quantum physics, and I failed, like everyone else, I guess. But I would try. I thought about how to do it, and I'm not going to tell you about things that you're going to see in the movies directly, but what I'm going to show you is one of the most bizarre things that you can find in the visible universe. All right, and I would just run with you through a certain physical experiment that you can do very easily nowadays in the laboratory. And this experiment contains everything, in my opinion, that is weird about quantum mechanics, because quantum mechanics is one of the weirdest things you can find. There's nothing more weird that exists. So let me start. All right, so let me start with the Hollywood, which I actually don't like very much. Sorry, Michael, but I think that Hollywood is a cheesy endeavor. But so Harry Potter, right? It's a book that sold 1 million copies, and the writer made a lot of money. Well, I never made this kind of money, so I'm jealous. But in this book, many people are thrilled about this book because there's a lot of, magic, and it looks like the author had a lot of imagination to come up with these things, right? And one of those things is, the guy shoots something from the magical wand, okay, some energy or some lighting, and it's supposed to be very cool, okay. And of course, there is a spell that precedes this kind of actions, right? And okay, well, it's cool, my 10-year-old daughters are fascinated by that. But I will tell you something more fascinating, right? Something that is real. It's not a book, but a reality. So Harry Potter is a wizard, right? And let me show you the real wizards, okay? So that's one of them. It's not the grand wizard of them all, but a wizard nevertheless. And he came up with a spell, right? That is here, right? E equals mc squared, and everybody knows that, right? It's abused and misunderstood, but it's a very powerful spell, okay? Because, Harry Potter shooting something with the wand cannot compare with someone who actually can deploy it in, for instance, atomic bomb, right? That can eradicate cities or even the whole planet. And if an asteroid is coming to hit us, right, probably people will send some atomic bombs to deflect its trajectory. Okay, so it's a very powerful spell, okay, right? Of course, you have to be initiated to understand it and use it, but nevertheless, it's a spell. All right, and let me show you another wizard, okay, which is a better wizard in my opinion, more fundamental. This guy, his name is Erwin Schrödinger, if you don't know. And actually, he's the founding father of quantum mechanics. Einstein was too, but Einstein had problems with quantum mechanics, whereas this guy didn't have any problems whatsoever. So this is the famous Schrödinger equation that is one of the basic equations that describe everything there is. Okay, it describes behavior of atoms and elementary particles. I am bending this a little bit now, but more or less. And if you know this equation, you can control the matter at the very basic level. Okay, what else can you have that is more powerful than that? You tell me. All right, so now let me show you. Now I'm coming to the meat of my talk. So let me show you a very simple experiment that you can do in the lab. And we do this kind of experiments in CQT. So I could, in principle, take you there and show it to you. But I can't, not here. All right, so this is a very simple thing. Let me go through it. And if you are not amazed at the end of that, that means that I failed miserably to show you the mysteries of the biggest mystery of the universe, but well, that will be on me. All right, so a very simple thing. Let's look at this. This is a photon source, okay? Photons are everywhere. This light here that shines on me contains millions of photons. You don't see them as individual particles, but they are particles nevertheless. And why they are particles? Because we physicists, we can attenuate this light and we can select single photons. All right, so there's a source of single photons, and if this photon travels here on the beam splitter is just a piece of glass, okay, that reflects 50% of the light and let 50% light through. Okay, it's like a window. If you look at the window at night, you can see reflection of yours, right? And you see also what's outside. However, a window does not reflect 50% of the light. It reflects around 18% of the light. But you can create a mirror, a glass, a slab of glass, that will exactly let 50% light reflect, and 50% of the light will go through. Okay? Now, if you shoot a single photon and you go to the lab, and behind this beam splitter, you put photon detectors. I'm not going to tell you how they work, but there are such things. All right? So you will see that every single photon has exactly 50-50% of chance of going to this detector or to this detector. This sounds very innocent, right? But it is an important ingredient of what's going to happen later. So the photon coming on a beam splitter is a perfectly random process, and there's no way, nobody in the universe, Harry Potter, Einstein, or Schrödinger, can tell you where a single photon emitted from this source will go at any given moment. It's not possible. Nature at the very fundamental level is random, okay? It's like flipping the coin, right? I dropped it, right? But it's exactly 50-50% of getting heads or tails, all right? Later I will collect it. All right, so you have to believe me that this is the case, but it is the case, okay? As I said, in the lab I could tell you, I could show you this. All right, so that's cool. So let's remember this, right? You send a photon on a beam splitter, and you have 50-50% that is reflected or it goes through. All right? Okay, now let me complicate this experiment a little bit, but not too much. So basically what I'm going to do, I'm going to put two mirrors that do nothing but reflect the direction of the traveling photon. Okay, photons travel with the speed of light. And let me put another beam splitter here. Okay? This is the same beam splitter as this one. Okay? It's very important. This beam splitter can be as far away from this beam splitter as you want. And moreover, you could put this beam splitter at the last moment. So when the photon flies here or here, you could put this beam splitter just before the photon arrives there. Okay? That's important. Just remember that. Okay. So now what's going to happen? Now I'm going to do a very simple calculation, okay, which is basic probability calculus. But don't be afraid, okay? It's very simple. All right? But as you will see, it will lead us to one of the biggest mysteries, as I promised at the beginning. Now it doesn't look like it's any mystery, okay? But you will see that, well, it is. All right. So let's take a single photon. So let's say the photon it goes here. Now suppose it goes this way. Okay, there's a possibility. If it goes this way, it will be reflected from the mirror, all right? And now when it arrives here, again, it can go with probability 1/2 here, or it can reflect here, right? Okay? So because here there was 1/2 probability going here, so suppose that we want to calculate the probability of the photon coming here. So it's a very simple calculation. 1/2 here, 1/2, and also 1/2 here. Because these are independent events, then you have to multiply those probabilities. So the chance that the photon coming from here will end up here is exactly 1/4. 1/2 times 1/2, the last time I checked, is 1/4. All right? But now, of course, it could be that it have gone this way. All right? In which case, we have 1/2 probability of going here, 1/2 probability of being reflected here. So it's again 1/4. 1/2 times 1/2, all right? So overall, you have here the probability of arrival 1/2, because you have to add probability of going this way and the probability of going this way, right? One more time, this way or this way. So two paths, each has 1/4 probability of happening. So the total probability is the sum of those probabilities, so you get 1/2. Okay, and of course, it's all very symmetric, therefore, the probability of a photon arriving here is also 1/2, sorry. Is it clear? I mean, this is a very simple thing, all right? Okay. All right, so you go to the lab, you set it up. It's easy, any PhD student can do it. Now, I think that even if you do master thesis in physics, you can do it in the laboratory, right? The technology is so advanced that this is a very easy experiment to do. Well, I've never been in the lab in my life, okay? So I'm just taking on faith, but I think it's easy. Okay, so one more time. In this setup, right, this is, by the way, called the Mach-Zehnder interferometer. So in this setup, you put a photon, and these detectors click the signal arrival of the photon 50-50, okay? So click, 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 like the coin, right, random coin. Okay, but now let's go to the lab and do this experiment, okay? So now, before that, right, there was this guy, another wizard, okay? Maybe it's politically incorrect that he has a cigarette, and something, probably alcohol here. But well, times have changed. So this is Richard Feynman, who got a Nobel Prize for his research in quantum physics. And he said, and you can find this on YouTube, he did say it. It's not some invention. Okay, he said that nobody understands quantum mechanics, all right? So let me just show you why. Okay. So here, this is what is happening in the laboratory. Before I showed you, right, what we predicted, okay, that would happen using common sense. Okay, in the previous slide, we just look at the photon. It's sort of behavior of the photon here is like a billiard ball, right? It can bounce around, and using this picture, we can predict that there'll be 50-50 here. All right, but actually in the laboratory, when you shoot a photon into such a setup, what happens is that this detector never clicks. Kosong. In Singapore, it means 0, right? If you go and order coffee in hawker center, right, and if you say kopi or kosong, you get the black coffee without sugar, okay? Sorry. So nothing arrives here. All the photons that come here into this setup end up in this detector. And you know, I could try to explain this to you, all right, but I decided not to, because that would be too convoluted, right? I would have to go to philosophy, I would have to go to bizarre interpretations of quantum mechanics that Michael mentioned, like many world interpretation. I don't want to go there, because then it's like trying to cheapen the whole mystery, all right? The fact that the photon only arrives here is contradictory to our predictions, okay? It's just counterintuitive, but that's the way it is. And I deliberately want to leave you with this, all right? Because nobody here in this room, not even Michael, right, or not even big professors wearing glasses and suspenders and beards, they cannot tell you exactly why it is like that. It is like that. Nature behaves like that. It's a paranoid behavior, because what it means is that the nature behaves in different ways depending on what questions you asked the nature. In this experiment, the question asked was, is the photon here or is the photon there? That was my question that I asked. Now, in this experiment, I asked, is the photon here or there, but I allowed it to travel in different way. So I set up different experiment. So basically, quantum physics is like that. The nature behaves this way if you ask this question, or it behaves that way if you ask another question. Right? And that's very strange, because in our world, it is not like that. Okay, if you ask the question, how many money you have on a bank account, you will get a definite answer, and this doesn't change whether you ask this question via internet or you ask this question via telephone, right? Or you go and check yourself on an ATM machine. Okay? The answer is the same. It's not so at the fundamental level. So nature is crazy. Okay? It just behaves in a strange way. And I know that probably I'm still have a lot of time or whatever, but I'm not going to bore you anymore. Okay? I just want to leave you with this, okay? Just so that you think about it, and you can ask me questions later, or you can ask Michael, right? Or you can go and Google it, right? But I want to leave you with this mystery, because, you see, the universe is a very strange place to be. Physics showed us that showed us that common sense, let me be a little bit rude here, is bollocks. There's no such a thing as common sense, right? Nature does not bend to our wishful thinking, okay? The nature is what it is, right? And we can probe the nature, we can ask questions, right? We can basically enjoy it, okay? You know, these things, right, this kind of questions, this kind of mysteries, they'll be always with you. Nobody can take it away from you. Not Donald Trump, not anyone else, okay? It is for you to just to marvel in it, because the world, it is a very strange and bizarre place, and science is one of the ways to show it to you. Another way is to just do arts, right? Arts also show you certain strange aspects of reality, okay? But physics is something that gives you a very precise tool just to enjoy the universe, okay? So please do enjoy the universe. And I hope that this shorts will be one of the ways to enjoy it. Thank you.
Thanks very much, Dag, for introducing us to some of those kind of questions that really make you think, and I hope that you are, as he says, going to enjoy this wonder of the universe. It is a strange place to be. So I see a few people have come in since we started, so I just want to say briefly what's going to happen now. So this is a special event for the screening of the Quantum Shorts Film Festival. We have 10 films that were selected from 176 entries. The two speakers you've just heard from, Michael and Dag, were both on the shortlisting panel. And we're now going to play those 10 films. They're each under 5 minutes long. If you picked up a handout, you've got some information about them there. And they'll be on loop. So that will take about 40 minutes altogether. At the end of that, please stay. We're going to have a panel discussion when we can take your questions, both with the speakers and with two of the team, people from the teams that were on the final films. So we have 2 Singapore films in the mix. Look out for those. Just one other thing. So while you're watching the films, we are also going to invite you to be part of the judging panel. So these are our shortlist. We still have final prizes to decide. We have a jury that's deciding 2 of the awards, but we also have a People's Choice Prize that's being decided by a public vote. So you can pick your favorite from the 10 films and go online. There's a link inside your handout to cast your vote towards deciding that prize. Okay, thanks very much. Enjoy. So, thank you all for watching these Quantum Shorts films. We're at the end of the 10 Quantum Shorts finalists in our latest film festival. We are going to have a panel discussion now with 2 of the shortlisting judges. Those of you who are here from 2 o'clock heard them speak already. Dr. Michael Brooks, who's a journalist and host of the Science-ish podcast looking at science and popular culture, and also Dr. Dagomir Zukowski, who's a principal investigator at the Center for Quantum Technologies and a filmmaker too. So we're also very lucky to have with us 2 members of teams that made some of the films you just watched. So maybe you spotted Heads or Tails and Slide were both Singaporean contributions. So I'm going to invite to join the panel Thomas Tay. He is the director of Slide. And he took a gap year from his university studies to pursue a diploma in film and television with the Singapore Media Academy. He says that was the most satisfying of his 23 years of life so far. So he's working towards his dream of being a filmmaker. So, and he's made a few short films so far. He says most of them have failed, a few have succeeded, and none of them were regrets. I also welcomed Chen Paishan. She's the screenwriter for Heads or Tails, an educator with a background in science. Her secret passion is for the literary and performing arts. She co-wrote and directed her first amateur musical during her undergraduate years and writes online fiction in her spare time. So she was recently placed first in Pitch Fest 2008, organised by the Singapore Screenwriters Association. Okay, I'm going to join them up on stage to moderate this discussion. We're going to start with a few questions. Sorry, I hit my microphone. And then they will be taking questions from you. There'll be a microphone, so please wait for that to come to you. Okay, so thank you, all of you, for being here. I wonder if we can just start by talking about the Quantum Shorts films that we just watched. And if you would choose one that you liked and something that you liked about it, and just describe that for us. So I'll start with my question.
Okay, it's quite difficult to choose one, and I won't choose Thomas's as he sat right next to me, and I'll tell him later how much I like that. I think for me, the one that stood out in some ways, especially watching it just now after Dag had said what he said, was Knock Knock. So this is the one where the 2 girls sort of have, basically it's an absurdist thing where a black hole knocks at the door, or there's a kind of concern that if you go outside it's going to kill you. And if you know a little bit about sort of what they're talking about this kind of understanding the universe and all the threats and all the difficulties and dangers that this massive universe presents to us, tiny little humans. And then, it ends with that absurd dance, which is, I think, their way of just sort of reflecting on what can you do about it, which is exactly kind of what Dag was saying about, this mystery of quantum physics. All you can do is kind of enjoy it and see something in it, and you can worry about it, or you can just kind of enjoy it. And I just like the way that they represented that in that film.
Well,
the short film, If the World Spin Backwards. It was a really good short film, and brought a lot of feelings out from me. I mean, we are quite fortunate that the world is working the way it is. I mean, scientists always say that Earth is a very special place. It takes a very special spot in the universe. And if any one of the conditions were not right, we wouldn't even be here right now. So I think that sort of resonates of what I got from If the World Spin Backwards. Like, if anything didn't work right, then a lot of things will be in chaos right now.
Maybe you ladies first.
Okay. I think I quite enjoyed When the World Spins Backwards as well as QED. I thought QED was quite interesting because it was like a human personification of a quantum physics concept. So it made it quite easy for the layman to understand. I'm not a quantum physics expert, so that was something that I quite appreciated about it.
So I also like the world spinning backward. This is the title because, you know, like Michael mentioned this movie Interstellar, and I think that in the Interstellar there was this terrible thing about time dilation, when the guy, you know, departs and comes back and his daughter is dying, right? That is terrible. Okay, it's a very emotional thing related to physics, and that film showed the same, right? With a very tiny budget, you know. And I wouldn't call it the world spinning backward. I would say what happens if the time flows backward. It's a better way to say that, right? Because then it's related to entropy and reversibility of physics. So that film for me was about reversibility of physics and then what would have happened then. And it is also very emotional. It triggered a lot of feelings in me, especially about love, right? When you see that you know all the love you have, right? But soon you will forget the face of the person you loved. That's very, very lyrical, you know. It's great.
So just before, please have your questions ready before we go to the floor. Thomas and Peishan, maybe I can just ask you to say a little bit about how you chose the storylines for your films. So maybe Thomas, you'd like to start?
I felt that quantum physics was a really difficult topic to begin with. It's really difficult to write a story about a science topic without a huge budget. So I mean, I thought a lot about the story for weeks, for months, trying to write something that I could actually produce, and I wanted to do something on parallel worlds, because that part of quantum physics is actually quite one of the easiest parts to understand about quantum physics. So the manual interpretations. So you've seen from the slide, you got world A, where this couple, the girl and the guy, but in the second world, they are a detective and a criminal. You know, they are sort of trying to get rid of each other. So you can trying to show audience that in parallel worlds things can be so much different. You know, yeah.
For our story concept, I was actually thinking about two different concepts. So one was this one, which was based on the Schrodinger's cat theory, and the other one was on quantum cryptography. But in the end, after discussion with the team, we decided to go with this one. Well, my main motivation for this sort of a storyline is, well, my background is as an educator, so I would like to make scientific concepts as easy as possible for my students to be able to understand, and that was where it all started. So I tried to come up with a storyline that made Schrodinger's theory something that someone who is not familiar with quantum physics might be able to relate to and be able to understand the theory in a simpler way. Yeah. So eventually we settled on this interrogation scene example, which I hope makes things slightly more comprehensible for someone who may not have a physics background.
Yeah, just to add on, I was also trying to show audience that interparallel universe travel is not time travel. It's two different concepts. Yeah, right to say it's different. Right? Yeah, it's not time travel. Anytime I bring this topic to my friends, then they'll be like, "Is it time travel?" No, it's not time travel. It's two different things. I think it'd be better if the guys on my side explain that to you.
Actually, you may not know that, but both of your films are the same.
Sorry?
Both of your films are the same, because Schrödinger cat can be resolved using many-word interpretation without this paradox of being alive and dead at the same time. So actually, it's the same thing.
Yes.
So I just mentioned we've got short interviews with all of the filmmakers who have made the finals on the Quantum Shorts website, which is shorts.quantumla.org. So as you saw, the films come from all over the world. I think we had 8 countries represented, so we couldn't bring everyone here today. But if you want to know more about the background of those movies, you can find that there. So I'd like to ask if anyone in the audience would like to ask a question. And if you do, please raise your hand and a microphone will come to you. You can either ask the panel, or if you want to ask any of the individual panelists a question, just make that clear at the beginning.
Is it on? Oh, yeah. I would like to ask, well, the academic, older part of the panel, how many issues do you have when you see creative people as well as anyone who's interested in communicating quantum mechanics to the public? How many problems do you have with this macroscopic or this projection onto macroscopic scenes of these physical principles?
Can I just clarify, do you mean talking about quantum physics as only applying to small things, or putting quantum ideas into these scenarios?
Yeah, I'm bringing quantum ideas, so these laws are trying to explain them using a macroscopic scenario that is supposedly more intuitive to human imagination.
But maybe, can I? Yeah, so you see, there's no fundamental limit where, let's say, Schrödinger equation ends. All right? It's a big mystery why there's a transition from classical from quantum to classical. After all, I cannot be in a superposition of 2 places, right? Which I would love to be, because then I could achieve more. But I can't be, right? So why is that? And of course, we don't know. There are some theories and there's discussion going on. But not so long ago, there was a very interesting experiment, exactly the one that I showed you, but not with photons, but with fullerenes. Fullerenes are really big molecules consisting of 60 atoms of carbon, all right? And these are really massive objects, and people showed the interference of those objects. Now, the next step was, and I know those researchers personally, the next step was to interfere a virus, okay? If they succeed to interfere the virus, right, then, the sky is the limit, right? Because there's no fundamental. It could be, for instance, the problem is with gravity such that we cannot kind of connect gravity and quantum mechanics. This has been a serious problem since the beginning, right? But nowadays people try to actually connect gravity with quantum mechanics, and it's progressing. So I don't see a problem, right, with the limit. The limit that the quantum finishes and classical happens. It's a vague. It's a vague thing. It's like, when you have the shore, when you have the ocean. Where is the limit between ocean and the beach?
Though with this transition not being scientifically clarified yet, do you think that there are some errors introduced by projecting this type of physics onto this macroscopic scale?
I don't think so. But
Yeah, I would say, as somebody who has to communicate quantum physics, you start, the whole thing is a problem, because actually really what you're talking about is math. If you're talking about the Schrödinger equation, you're actually talking about maths, and then you sort of do the maths and you kind of work it out, and the maths tells you that you can have these different probabilities of things existing in different states, and you can work it all out. And yes, you can do experiments and you can show that these things do impact the real world. But as soon as you're talking about anything to do with quantum, talking involves language that doesn't have the concepts that actually the maths has, in a sense. So I can talk about a quantum particle, but I could equally talk about it as a wave. And the fact is, our experiments show that it's not really a particle and it's not really a wave, and it's something else, but we don't know what it is. And I could call it a wavicle, but that doesn't help anybody. And so we're in a situation where what we're trying to do, and what Richard Feynman tried to do, what everybody since has tried to do, is say, we don't really understand it, but here are some ideas and here are some illustrations that, as you say, sort of intuit the kind of things that we're talking about. And that's what I like so much about the quantum shorts, is that you get these films which just play with these concepts. And they're as valid as anybody else's sort of concepts. So when you see the fullerenes, the carbon-60 molecules, and they go through this situation where they're effectively in two different states at once, and then we talk about them being in two different places at once because they go through a sort of double slit. And at the same time, I'm uncomfortable with saying they're in two different places because I don't know what it is that I'm talking about, because I visualize them as these carbon atoms and they're like particles, but they're behaving like waves. And if I do a different experiment, interpreting the kind of wave behavior, I get a different kind of thing. And all we're trying to do is play with these things and play with the language and play with our ability to interpret what the maths tells us. And somehow we do our experiments and it confirms what the maths tells us. But there's this huge sort of gulf in our understanding of what it actually all means. And so, we can explore it in films and we can sort of explore it in stories. And effectively what I do is tell stories about these quantum experiments. And I put some kind of interpretation on what I'm saying these things are. And I can talk about, these fullerenes as particles or waves, and I don't know which they actually are. And all we can do is kind of, play with these kind of concepts. And I think it's, that's one of the ways in which I think, and Dag makes films that do this as well, that kind of play with these concepts. And that's all you can do, because it's kind of, like he says, it's there to enjoy, it's not necessarily there to understand. So I think these are kind of graspings at what's real, but we don't really know what's real.
Actually, if I may add something, because I'm doing this kind of foundational research, right? So believe me that it can get violent when people discuss different concepts, right? Like this many-word interpretation, right? Actually was introduced by Hugh Everett III. Okay, was a PhD student of Wheeler, and he actually did not call it many worlds. Okay, he called it relative states interpretation. Okay, and then it was solid mathematical work. Okay, which interpreted quantum mechanics in a certain way. But after that came Bruce DeWitt, and he called it many-word interpretation. All right, and now I'm telling you that there are some people in the community, professors, scientists, right, glasses, suspenders, and beards, right. If you tell them that you subscribe to many-word interpretation, they will leave the room. Okay, or something worse will happen. Okay, so it is the community is divided, and it's good because it's like Michael said, this cannot be understood really. So there are no words. You have to do the math. All right, the mathematics is the key to comprehend it somehow, right? But there are no human words that can describe it. So it's fascinating. It's really cool.
Just to clarify too, the quantum shorts, in case it wasn't clear, they're not meant to be documentaries that are teaching quantum concepts kind of ab initio. I mean, it's really there to be inspired by the ideas, and then hopefully, if there were some concepts in there that you didn't know about already, maybe you do go away and Google it. And I mean, there are a lot of educational resources that will explain that. And don't try the Schrodinger's cat experiment on your friends, for sure. But this is about making people interested and starting those discussions rather than about necessarily directly teaching. We did a survey a few years ago where we actually asked our audience, how do you respond to these films? And you're like, do they make you confused about these ideas, or do you feel inspired or creative? And actually, we had very few people saying, oh, now I'm more confused than I was before. So I hope that this is also true of those of you who are here today. Maybe we can take another question. Does anyone want to ask something from our filmmakers, physicists, or judges? Okay, well then maybe I have a question. It's quite noticeable to me that the films are all about these big ideas, the many worlds, and superpositions, arrow of time, and yet you hear a lot of work on applied things, technologies, cryptography, and I wonder, is it just harder to make a film that has a technological idea in it rather than a concept? I wonder if anyone has any thoughts on that. Why was it you decided not to make a movie about cryptography?
Well, the cryptography idea that we had involved, it was based on the Alice and Bob concept, and we thought about personifying this Alice and Bob, since they've given them human names, so we thought that we could do a sort of personification of that. But when we thought about how the narrative was going to flow, it sounded like it might be, the idea that we had might be a bit less interesting because it would just be one main character. So I think that concept needed a bit more thinking through before we might actually consider putting it on screen. So that was why we eventually chose a different idea.
As you make films about big ideas?
Look, what sells, right? Sex and violence, right? I did try that, didn't work for me. I think that because quantum technologies are, maybe they're not so, the cryptography is boring for laymen, I guess, and I think quantum mechanics has this problem that if you want to make a film about it, it must be a weird film. It cannot be normal because it is a weird theory. It's much easier with gravity because gravity is more palpable somehow, right? You have black holes, you have objects that really are there, you can see them. I don't think the black holes were photographed, but we know there's evidence for them to be out there. So it's some kind of more, you can touch it, right? Whereas in quantum physics, there are these weird things that cannot be really explained. So technology, maybe quantum computers, right? Quantum computers is the thing of the future, right? IBM, Google are investing in that heavily. So they are there already, okay? They are primitive and not doing much, but that's probably a transition period. And quantum computers are strange, but I think that somehow I don't see it. It's difficult to make it about technology, right? That wouldn't be already. I don't know how to phrase it, but it'll be boring, I think.
I feel that there's in terms of filmmaking, right? There's a balance. When you watch a film about sci-fi, right? Audience go to the movies, they expect to see all the nice effects, all that. But then, because people, even though with those special effects and stuff, people might not even even if it's based on quantum ideas, people might not even like the film in the end, even with all the big, huge budget put into the film. But what the film that works, right, are the films that with the content ideas, right, you package it with a very nice story. So people write stories based on these ideas and they sell it to the audience. I think those are the films, even without big budget, those are the films that can work under sci-fi. So, like Back to the Future, you really think about it, there isn't really like when in Interstellar where there was a black hole or stuff. Back to the Future was an old car, 88 miles per hour, and lightning effects, all this, but people still like the film. Trying to create the 1958 or the year 2000, those set design those are difficult, but if you compare it to films nowadays, right, even with those special effects, people might not like it. Yeah.
I think story is everything, isn't it? And when you're just talking about introducing a technology, you don't really have a story to tell about it, except, there was the nice film that has the kind of legacy of the quantum revolution, the Spanish film, and it sort of talked about how the technology transformed society and Silicon Valley was dead, and there was the new kind of quantum technology, and even a kind of hint that it created almost like a new religion, a new pilgrimage kind of thing. And so there's a story there built around technology, but like Dag says, if you just look at one technology, it's kind of dull. And people want to connect with your film rather than just look at a technology.
ask a question, anyone in the audience, please put up your hand now, because I think we're coming up to the end. Okay, we've got one here.
Hi. Yeah. So I sort of have a two-part question, I guess. So one was just, maybe one's a bit of an observation, more of just, why can't I infer some state of events from Schrodinger's box? I still don't get that bit. Can't I infer after I check that something obtained before I checked? So that's kind of one of the big confusions I've always had about that issue. Right.
Not on you.
Sorry?
Not on you.
Oh, okay. So kind of following from that, it sounds like a lot of quantum physics just stands in complete defiance to any sense of logic that human beings as perceivers have. And I'm kind of wondering, as physicists, is there kind of a moment in film that has been able to provide a visualization of something as paradoxical and as kind of a like that breaks just all of the categories of the mind kind of thing? Has there been a moment in film for yourself that has been able to give you that visual illustration of a particularly difficult concept? Yeah.
I'll go first, and then everyone else can give a better answer. I think the first question is really about the measurement, or once you've opened the box and looked at the cat, you've done something called that is sort of classed as a measurement. And in quantum physics, measurement actually changes this kind of situation that you've got. So there is, Niels Bohr kind of said that until you do a measurement, all things are possible and all possibilities are real, or nothing is real, depending on how you want to look at it. And when you open the box and look, you change the state of the system. And again, it's kind of, it's a fudge, really, isn't it, from the maths? You can do the maths, and the maths is there and gives you all the possibilities and probabilities. But quantum physics doesn't really have a good way of defining measurement. So it's not just you that's confused. It's the whole field really has avoided this issue, I would say, for sort of close on 100 years. So nothing is probably going to change anytime soon on that. As far as films that demonstrate difficult concepts, I found Inception to be really sort of mind-bending in terms of the world that they create inside somebody's head, and go inside in these kind of layers. And I guess Nolan is very good at that. Memento is another good example of a film where you're just like, what? Yeah, so Inception would be my one. And I mean, a film about dreaming that sort of messes with your mind that much. My mind actually shut down. The first time I saw Inception, I saw it at the cinema and I fell asleep. And it was like my brain just said, nah, I'm not having this. And just like, I fell asleep. And then I've watched it sort of 3 times since and sort of gradually get my head around it. And the other one that I really liked that sort of messed with me was, again, another kind of neuroscience-y thing. What's it called? Eternal Sunshine of the Spotless Mind. Where you're trying to erase memories and you're trying to work out what the filmmaker's saying at any particular point. And I think those things about sort of what's inside our head and how memories exist and how we categorize stuff and how we forget things and whether we can forget things, they certainly get to me, and break my mind.
Getting back to your question, right, so as Michael said, the problem of the Schrödinger cat is not resolved. I mean, it depends on the interpretation, right? There's Copenhagen interpretation by Niels Bohr, which is a very pragmatic and for many people boring interpretation, right? And then there is many-word interpretation. So in many-word interpretation, this problem is sort of solved, right, at the cost of multiplying the universes, right? If you're okay with, multiplying universes every time you flip the coin, be my guest, right? But in this interpretation, there is nothing strange because the moment you open the box, right, the world splits into 2. In one world, the cat is dead, and you see the cat is dead. And in the other world, the cat is not dead, and you see he's not dead, right? It's not dead. And then the paradox is resolved, right? But at the cost that the universe had to split. And every time something happens, it splits again and again and again. So it's a terrible, cascade of universes, right? Which is probably not so cheap, right? But somehow, if you accept this, it's okay. So, and the second part of the question, right? I think that, as I said, right, movies about quantum physics, they have to be strange because there's no other way. And then it's up to you whether you get the flavor and you enjoy it, right? Or you don't get the flavor and you're bored, right? And there's no other way, I think. unless you want to attend one of my lectures or someone else lectures on quantum mechanics, then yeah, but that's not a film. Yeah, there's no drama there.
Do you want to nominate a film?
Sorry?
Is there a film that has
Oh yeah,
made a
I'm not
positive
qualified to answer the first part, but for the second part, right?
Nobody is here.
Yeah, no.
Don't worry.
But for the second part, I feel that a lot of superhero films actually touch on this subject. Like, if you all Flash, the TV show, if you all watch Flash, right? You know, when Barry created a flashpoint and all these stupid things happen, right? Those are the moments that make me think that if I had the choice to go back time and change decisions, and will I be able to bear all the consequences and stuff? Like, those are the moments in TV or film that shows the how story can be so good, written based on a scientific theory. And you can try Ant-Man at the Wasp. You know, when Ant-Man travel into the quantum universe, like, I mean, the artistic team, I think they spend a lot of effort to design the scenes for the audience. I think they tried to base it as close as possible to the current interpretation of how it will look like. So, and you get to have fun at the same time. You get to laugh at the same time. So, I think this superhero films, this aspect is a very nice place to start if you want to appreciate science and also have fun watching TV and films at the same time.
Well, for me, I think one sci-fi film that got me thinking was Interstellar. So the thing about that was there was the idea of these astronauts, like, I mean, traveling to a different part of the universe, and then time is different in different parts of the universe, depending on like something about gravity, but not an expert about that. But because I am a biologist, so biology is something that is a bit more concrete and less abstract than physics. And I kept trying to reconcile the concept about aging in terms of our biological body and how that links to the concepts of space and time, which is something that is very abstract. And that link was something that I thought was quite difficult for me and for the friends that I had this discussion with. And honestly, I still don't have a good understanding on how exactly aging is affected, or how our cells' developmental process is affected by the different, well, time-space conditions in different parts of the universe. So yeah.
Actually, just to drink for that, right? Just coffee. You know, if I put this cup here, right? So my brain is higher than a cup, right? So the gravitational field is a little bit less than acting on the cup, right? So actually the time for this cup flows different than the time for my brain. Of course, the difference is negligible, right? It's unobservable probably. I would have to calculate it, right? Which I forgot how to do, by the way, because I do quantum mechanics on gravity. But there's a difference in time flow, okay? So I think if you want to be a little bit younger than me, right, then you have to move up slightly. You know? So it is strange. It is a strange world, really, indeed.
Stay in the mountain area.
Yes, then it's better for you.
top level flats?
Correct. Also better air.
Okay, I'm afraid that we've run out of time for our session today, but thank you very much all of you who are here, and a special thanks to the museum for hosting us and to our panelists, Michael, Thomas, Dag and Pei-Shan. I think we'll be here a little bit longer. Some of us, if you want questions answered that you weren't brave enough to raise your hand to ask, please come up and ask us now. And thank you again, everybody.
Thank you.
Oh, yeah, you can go towards it.